This video is for the product and quotient rules for derivatives. I'm going to start out with limits. Review a couple of properties of the limits here. That the limit as x approaches c of two functions multiplied together would equal the product of those two individual limits multiplied together. Same rule applies for division. The limit of a quotient is essentially the quotient of the limits, with one obvious exception there is that the limit in the denominator cannot equal 0. Other than that, they're equivalent. However, this is very, very, very important right here. I cannot stress this enough. That property is not true. Either of those properties are not true for derivatives. We're going to see that the derivative of products and of a product will not be the product of the derivatives. It would be nice if it were true, make things easier, but since it's not true, we have to deal with what is true. So now, let me show you this little example here. One example is all it takes to show that it's not true. You can certainly prove a contradiction to an argument real easily by finding one example that's not true. Finding an example of a situation that is true doesn't prove something is right, because it could have just been a fluke, whatever particular situation you were using. Might have been just an accident. But it's easy to prove a contradiction here. So, like for this one, if I was going to take the derivative of x squared times x cubed, there's no doubt I can multiply those two x's together using property of exponents and get x to the fifth. And therefore, the derivative of x to the fifth is definitely 5x to the fourth. Now, what if I did split these up? I took the derivative of x squared and the derivative of x cubed separately. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. Multiply those together, we get 6x cubed. That is wrong. You see it doesn't equal the correct answer. But see, this was kind of convenient, because you could multiply the two x's together. Well, in most cases, but what if we had something like this? We need some sort of, so if I'm saying that you can't take the individual derivatives, how do we do it? It's like, for example, y equals x squared cosine of x. All right, well, good question. We probably need some sort of rule that will allow us to take the derivative of a product of two functions. And surprisingly enough, it's called the product rule. Wow. All right. Zoom in on this. Now, I kind of use shorthand notation. And yeah, it's not, you have to know this rule, but you don't have to memorize it exactly in this form with all this. But anyway, the derivative of two functions f of x and g of x it's f of x times the derivative of g of x plus g of x times the derivative of f of x. Now, I often use this shorthand notation right here, so we won't have to write all the x's out there. And of course, it could even be a different variable. It could be like d dt of f of t and g of t. So I'll put like this: fg prime plus gf prime. I often do it this other way, because notice that since this is addition between the two terms, you can reverse them. It's the same thing. I even switch these two around. So you'll see the examples I do, I often work it this way. But obviously, the original form is correct also. Both of these are correct. So I often treat the product rule as f prime g plus fg prime. Like I said, you can obviously do it the way it's originally defined. So now okay, well, first of all, let's obviously check at least that it works. Once again, this won't prove that it's right, but it is right. But obviously, it better generate the answer that we know already for this problem, so we can feel better about it. Someone else has already proved this theory, so if you take x squared and x cubed, call it f and g, and if I go this order, f prime g plus fg prime. The derivative of f would be 2x. The derivative of g would be, not g. It's just g here, not g prime. So it's f prime and then g as is, plus f as is, which is x squared, times the derivative of g, which is 3x squared. So 2x times x cubed would be 2x fourth. X squared times 3x squared is 3x fourth. Add those together, 5x fourth, and that's definitely the answer we got before, so that's the correct answer for that derivative. I say that's not the proof. Here's the proof, which I do not worry about this. I just copied this from the book. If you're fascinated by this, feel free to take a look at it. Personally, if I was taking obviously these videos are for all my classes, but if I was taking a 4-week class, I certainly wouldn't feel like I would want to invest any time studying this. But anyway, well, you do what you want. So it's taking the limit definition, and it's having to do some stuff here where it's having to subtract and add to, because obviously those would cancel and blah, 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 yeah, blah, blah, and you end up with that result. So that is not important that you know this at all. Just know the f prime g plus fg prime. All right, so then the derivative of y equals x squared cosine of x. Like I'm using my order I like to use, but like I said, if you do the other order, that's okay because of the fact that it's plus in the middle. Let's see what we have here. The derivative of f is 2x. G will just be cosine of x plus x squared, and then the derivative of cosine we learned before is negative sine. Now you could, make sure if this was a handwritten exam that you either put parentheses around it. Don't put it without parentheses because it would look like it was subtraction. Or the minus could go out here and it could look like this: x squared sine x. And then you wouldn't need parentheses, so either one of those would be correct. Oh, maybe I should give it a little happy flag there. We like it. All right. Okay, so there we go. I wouldn't worry about having to get too fancy on simplification. I don't know, some solutions to problems and practice problems this one I can't imagine they would do it, but I don't think you have to worry about oversimplifying too much. In some cases we will, but all you can really do here is factor out of x. Now, there'll be some problems where we're taking this and we're setting it equal to 0, and then we would want to factor stuff out, but not just for the derivative itself. Now, this one's kind of interesting because you can kind of go about this one 2 different ways. The last problem we had to use the product rule, but technically you could, for this one, you could FOIL out f and g first and then take the derivative. Well, that's okay. We'll use the product rule because it's new, it's exciting. So, but I wanted to mention that in case you were thinking that. Could I just multiply that first? Yes. All right, the derivative of, so that's f prime right here. The derivative of 3x minus 4 will be 3, and there's g, x cubed plus 5, and then f, which is 3x minus 4, and the derivative of g is 3x squared. So if we don't have to simplify, then we would stop right there. If we did simplify, we would just distribute these terms and just combine the like terms, and then you would end up with this answer right here. So that's just a simplified version of the other answer. But, you'll only do that if you need to. So it's not something you have to do all the time. Well, how about this next one, the square root of x times sine of x? Well, we absolutely have to do the product rule here. There's no other way. And I'm specified do not simplify. And, all right, the square root of x is x to the 1/2. So you bring the 1/2 down, makes that negative 1/2, and then times sine of x. plus f, which is x to the 1/2, times the derivative of sine, which is cosine. So basically that's it. I just did it in Maple for the heck of it, and Maple just dropped that x to the negative 1/2 back down and called it square root of x on bottom, which is fine. But same answer, it's correct. Now this, what Stewie says here is more appropriate for handwritten exams that I would give in a face-to-face class. Is that I might have mentioned this in another video, but it's important for derivative to have derivative notation. So in other words, if you were writing out an answer, and this is good information. Suppose you take an online class from me, and then you move on and perhaps take a face-to-face Cal 2 in a different format. So I think that could be helpful for you also. See how your instructor feels about that, obviously. But I always like to make sure, because I don't like to have it with just the part to the right of the equal by itself. It needs this. Now, if somebody put y prime there instead of g prime of x, I would be all right with that. I just want something over there that, like that represents a derivative. So for anyone that's taken this class in my online format, that doesn't apply, but that's good information to know, I think, for the reasons I was explaining. Who knows, you might come to my face-to-face Cal 2 class. I've had people do that. Quotient rule. Well, we learned that the derivative of a product is not the product of the derivatives. Same thing for quotient. Boy, it sure would be nice, if you took it'd be nice if the derivative of f divided by g, was f prime divided by g prime, but it's not. I'm not sure if I copied the proof out for this one too. Oh, I did. Okay, once again, the proof is not needed for you to have to worry about learning, but if you're interested, feel free to take a look at it. You'll need to know this formula, though, not perfectly memorized, just you need to know it and enough, to be able to work with it. That's all I'm saying. When I say memorizing it, you don't have to spit that back out exactly. Just know this, enough of this right here. So f over g prime is defined as the g times f prime minus this time in the middle, f, and then g prime here. Now this is very important. Unlike the product rule, which had a plus, we could actually do those in either order for the product rule, but you got to keep it like this. No order for because of the minus there. You can't just change the order around. I've had people miss quotient rule problems on tests because they'll do the f g prime first and then the gf prime second, and they'll get the numerator backwards, and they'll be off by a negative sign. That's what will happen. So I'd hate for you to pick the wrong answer for a problem if it was multiple choice, because if you reverse that, the negative answer might be one of the choices. So the rule of thumb is don't reverse that. Oh, then all that's over g squared. Forgot to mention that. Provided that g of x is not 0, which obviously the original function is not going to be 0. So this right here. So I've seen it in some books, or some people talk about, where you can think of it this way, whatever way helps you. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. I've heard another one where it's called like this. Where you put the original fraction as, and don't worry about all this. But I've had students that maybe they were exposed to calculus in high school or something, and oh yeah, we did it with low d high. Derivative of high would be f prime. Low d high minus high d low over low squared. What? Okay. So whatever. If you have a cute little naming, like I said, you don't have to, you just have to do the quotient rule on a test. You don't have to write it in a certain way. So if you enjoy cute little naming rules like that they help you, I'm all for it if it helps you. So it'd be low d high minus high d low over low squared. All right, here's an example. I'm going to show you what the derivative is and then show you using the quotient rule. So let's say our function was x to the fifth divided by x squared. Well, there's no doubt that x to the fifth divided by x squared is x cubed. And there's no doubt that the derivative of x cubed is 3x squared. So therefore, the derivative of x to the fifth divided by x squared has got to be 3x squared. So I'm going to show you over here in red that taking the, that's not f prime g prime. Derivative of x to the fifth is 5x4, x squared is 2x. That simplifies to 5x cubed over 2, which is obviously not 3x squared. Let's do it using the quotient rule. It's the bottom, x squared, times the derivative of the top, minus the top, which is x to the fifth, times the derivative of the bottom, which is 2x, over x squared, the bottom squared. So the numerator is going to be 5x to the sixth minus 2x to the sixth, which will be 3x to the sixth, over x to the fourth, which is 3x squared. That's the correct answer. Like I said, there's the proof. Find the derivative using the quotient rule. Do not simplify. When you have like these binomial terms, trinomial terms, you're never going to have to FOIL out that denominator. Worst case scenarios, you might have to, and problems we'll see later, like say when we're solving these as equations equal to numbers, you'll have to clean up the numerator a little bit. That we'll have to do that, but in certain cases. But usually, just taking the derivative, we don't need to. But just kind of, if it's multiple choice, you'll be able to tell what's going on for sure. If it's handwritten, you would just be looking for my instructions that say do not simplify. So bottom times the derivative of the top, f, which is would be 6t, minus the top, 3t squared minus 1, divided by the derivative of the bottom, which would be 2, all over the bottom squared. Now here's another Stewie situation here. Yeah, a very common mistake here is people will cancel these. Well, they'll cancel the one on the top and leave one on the bottom. You cannot do that unless it was multiplied because of that minus sign right there. Let me come over here and write this. A minus B over A squared. Now, if you split that up into two fractions, then you could reduce that into 1 over A. But my point is, you can't cancel it in this form and leave it as one fraction. You could not do that. Because I think people will mess up, simple stuff like this. Now, they'll confuse the idea with this idea. Let me change it to, now, if it was A times B over A squared, then you could do that. You could do this and this. But not with that subtraction right there, which that subtraction is going to always be there, the quotient rule. So don't ever cancel those out. Stewie is a wise man. He knows what he's talking about. And let's say, okay, suppose that we did simplify the numerator. Okay, that's pretty easy algebra. I shouldn't have to explain too much there while I'm doing this. Combine like terms. And it will end up being 6t squared plus 30t plus 2. So that's all we would do if we needed to do that. Okay. All right. So we've introduced the two primary rules of this section, and now we're just going to look at examples, and we'll see some other stuff coming up here relating to this. Well, actually, I think there's one other. Oh yeah, higher order derivatives. It's not in the title. So there is a couple of new concepts coming. Well, one for sure. So we'll do this. Let's come down here. Cosine of t divided by t cubed. So it'd be bottom t cubed times the derivative of the top, which is negative sine of t, minus cos of t times the derivative of 3t cubed, which is 3t squared. Then on the bottom we have t cubed squared, which will be t to the sixth. That's actually that's correct. There is the derivative. If we wanted to get fancy, I mentioned that we won't ever have to square out binomials or anything in the denominator, but we might have to do this where that's not too bad to do this. You don't have to like FOIL out a bunch of stuff, call that t to the sixth. So technically, that could simplify a little bit. I mean, the answer in pink up here is good. But you could factor out a t squared from the numerator. That's the key. You can't cancel like this, but notice they both have a t squared that can come out of there, and then you have a t squared you can factor out of the bottom. I just wanted to show you that in case we needed to do that. But the basic derivative itself was not difficult following the quotient rule. So I did this in Maple. Maple, obviously it's going to give you the correct answer, but sometimes it gives weird looking answers that don't necessarily look like how a normal human would work it out. It'll do some weird stuff like this, for example. So if you kind of do it like I did here, there's a symbolic command to kind of combine it, and then it makes it look like that answer. Now, it just has it. Now they factored out a negative though, so if you factor out a negative, then that leaves which is not important that you do that, but that's what happened here. So he factored out a negative from both of these, and it made it a plus right there. So, all right, not a big deal. Okay, this one we want to find f prime of x and then find f prime of 3. So now we're going back to the concept of finding slopes of tangent lines, but now with derivatives that are requiring product and quotient rules. So it's a previous concept applied to a new type of derivative. And this one said simplify the numerator specifically, so we will. And it's real easy to simplify this one. Yeah, I don't like for the simplifications to be too complicated, so. Bottom, x plus 4, times the derivative of the top, which is 1, minus the top, which is x minus 4, times the derivative of the bottom, which is also 1, over the bottom squared. And you multiply this out, what happens is the x's are going to cancel. And I've seen some people make the mistake of canceling the 4's, but keep in mind, it's actually 4 minus a minus 4. So really it's 4 plus 4, which leaves 8. So the derivative is f prime of x would equal 8 over x plus 4 squared. Don't worry about the bottom. That's why I said simplify the numerator. All right, now then it's super easy once you get that derivative. Just take the 3, plug it in for the x, bingo, you got 8 over 49. And just for grins, I graphed it, and there I kind of sketched a tangent slope. So, yeah, it's kind of flat, it's kind of positive slope, so, yeah. That looks about right. Well, I mean, I can't eyeball that and say, yeah, it looks like 8 over 49, but it's a small, flat slope, so I like it. Close enough. Close enough for me graphically that our answer is probably right, and it is right. Okay, here's just a quotient rule: do not simplify at all. Yeah, I've been known to have these on handwritten tests. I don't know I can't remember what I do on an online test, but if it is simplify, it won't be overly complicated. This is just seeing if people can apply the quotient rule. Bottom times the derivative of the top. The derivative of the numerator would be 2x plus 5 minus the top function times the derivative of the bottom, which will be 2x, all over the bottom squared. So technically, this answer, f prime of x equals this, that is the derivative. But yeah, you could plow through that numerator and simplify a bunch of other terms. I mean, but that's only if necessary, and I don't see it being necessary for this particular problem by any means. But well, we've seen in a previous section how to find the derivative of sine and cosine. Now let's look at the derivatives of the other four trig functions. So you do need to know the derivatives of all the 6 basic trig functions. You need to kind of memorize those. So with a little practice, you should learn them. Now you might wonder why weren't these derivatives included when we did sine and cosine, which would be a valid question. Well, the reason for that is these other 4 trig functions are actually reciprocal functions. They're fractions, like tangent sine over cosine. So to see these answers here, you would need to use the quotient rule. In fact, the quotient rule can derive any of these. So if you let's say if you couldn't remember, the derivative of tangent was that equaled secant squared, but you knew that tangent was sine over cosine, and you could do the quotient rule, you would come up with 1 over cosine squared, which is secant squared. So you could derive any one of these if you had to. But I think it's better just to learn them. So tan is sec squared. Derivative of secant is secant times tangent. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant times cotangent. And there I wrote the other 2 that we've learned before. And here's a little trick you may find helpful for helping to memorize these. Sometimes you might forget whether it's a plus or minus. You think, I know the derivative of cosecant, something to do with cosecant, cotangent, but I can't remember that it's whether it's positive or negative, and you don't want to, do the quotient rule with 1 over sine. Here's a little trick that if the trig function you're taking the derivative of, if it starts with the phrasing co, like cotangent, cosecant, even though you don't see an O there, it's cosecant, and cosine. Anything with a co in front of it has a negative derivative. Negative, negative, negative. So there you go. Maybe that'll be helpful for you. So work on learning those. And I just did one of these. I copied the tangent one from the book. So I just did the secant one. Like I said, I'm not going to spend a lot of time on this, but because if you want to ask me about it, that's fine. But I figured as long as you know it's sectan, then you don't have to even worry about doing this. But there's how you would do it if you forgot it and you wanted to do it via the quotient rule. All right. Okay, so let's look at some derivative problems now about y equals x plus cotangent of x. So y prime would be 1 minus cosecant squared. Yeah, obviously, as I'm doing these problems, I'm understanding that you don't have those committed to memory yet, but I won't keep scrolling back up there, but you know where they're coming from, obviously. They're coming from those rules we just looked at. So for this next one, I've got a quotient rule going on, secant of x over x. So you have bottom x times the derivative of the top. Derivative of secant would be secant tangent, minus the top, which is secant, times the derivative of the bottom, x, which is 1, all that over x squared. And that's it. Do not cancel the x into the x squared, as I explained before. I know you might have the urge to want to do it, but do not do that, because it would be wrong. Because of that minus sign in the middle, right there. Oh, an alternative way to do this problem is using the product rule. Now, if you're taking a multiple choice test, this is where you'd want a quiz or exam, you'd want to look at your answers and see what form they're in. Obviously, if the answers are kind of in a fractional form like this, you should apply the quotient rule. Although you could do the product rule and then convert it to that, but it'd be much easier if you did the quotient rule if the answers already look like that. On handwritten, I guess if I tell you to specifically use the quotient rule, then that's what I would be grading it on. Otherwise, if it just said find the derivative, whatever, you'd be free to do it either way. So this is just bringing the x up, calling it x to the negative 1, and just doing the product rule here. F prime g plus fg prime. So the derivative of x to the negative 1 would be negative x to the negative 2. And then times g, which is secant, plus f, which is x to the negative 1, times the derivative of secant, which is secant tangent. Now this next one, I wouldn't ask, two product rules on the test with same problem, so I'm not going to spend a lot of time with this one. Although that's what it is, it's two product rules. I'll just mention a couple things here. Well, of course, the derivative of secant is secant tan, and the derivative of tan is secant squared. Now this, I'll mention one thing, then I'll move on from this one. Now, if you want to look it over, it doesn't hurt. It's how to handle that 5. You could put the 5, outside and then take the derivative of this, and then you'd have the 5 in front. Which that's okay, but the problem with that is you would need to remember to, well, as long as you left the 5 and put it in parentheses, that's okay, to indicate that it's being distributed back through everything. You'd have to remember to do that, show it that way. But frankly, what I would just do, and that's what I did right here, is I just left the 5 with the theta together and let f be all of that. Let f be 5 theta. So therefore, the derivative of 5 theta was 5, and then you had 5 theta right there. So, yeah, but mathematically, you could pull the 5 out, because we've learned that one of the derivative properties is that if you have a constant multiple times the derivative, the constant multiple stays there, and then you can take the derivative. But in this case, you can also leave that multiple with this variable right here. So that's also correct. That's what I would do. But if not, you'd have to make sure your 5 was out here like this, and then you'd have this like that. That's all I'm saying. All right, so that takes care of that. Find the equation of the tangent line at a given point. Yeah, I've kind of always been meaning to revise my notes here, but okay, it's too late now that I'm making a video. Well, I can revise the notes later, but because I should have just done this. You see this problem going back up here. Yeah, this derivative is very similar to this derivative, so it's really not giving you much of a distinction here, but that's okay. As far as a variety of a type of problem. But the question's asking, now we're expanding this to, we're trying to find the equation of the tangent line at a given point. So the technique's still going to be the same. It means you need to find the derivative. It's just using the quotient rule now. Plug in 4 for x, and that will be our slope. And then we'll use the 4 and the 7 and the y equals mx plus b. So bottom times the derivative of the top makes that 1, minus top times the derivative of the bottom, which is also 1, and over the bottom squared. So the x's cancel. You have negative 3 minus 3. That's not 0. It's negative 6. One thing to keep in mind, the only way that would ever get 0 as a derivative is if there's any kind, like I said, it's f of x, and there's any kind of x there, you're not going to get 0 as a derivative. Remember, the only thing that can lead to 0 as a derivative is a derivative of a constant. Like if f of x equals 6, then that derivative would be 0. So yeah, as long as you have the variable there, the derivative can't be 0. Now, the derivative after you plug in a number could be 0, but not I'm just talking about algebraically, it can't be 0 right here. All right, so the slope is going to be f prime of 4 over here. So I plug in 4. 4 minus 3 is 1. 1 squared, yada, yada, yada. Negative 6, that's our slope. So we know we're looking at y equals negative 6x plus b. We know that x is 4. We know that y is 7. Plug in 4 for x, 7 for y. Solve for b. and add 24 to both sides, so it's going to be 31. Your y-intercept will be 31. So y equals negative 6x plus 31. And just for grins, I graphed it. This is your point 41, right? Okay. That's why I copied the scale thing out of the calculator. Excuse me. It's the 0.47. Look right there. The y scale, I did it as 7 on purpose, just so that makes sense. So that way it would hit right at a tick mark. I didn't have to like approximate where it would be. So the scale 7, so that one unit up, one tick mark up represents 7. So that is 4, 7. So there's your point. Yeah, see, that's a pretty good looking tangent line running right along that point there. You see it just clipping it right there and then running. Yeah, so that's perfect. So that probably means we're A-okay here. Yes, that graph would have been confusing if I had not included the scale here. All right, here's a trig one. Kind of a weird answer, but that's okay. Maybe I should have graphed this one, but that's all right. F of x equals x squared cos x. So let's do the product rule. Point pi squared 0. 2x cos x plus x squared negative sine of x. That's good enough right there for the derivative, because now we just have to plug in pi over 2 everywhere there's an x. Cos of pi over 2 is 0, so it wipes out all this. Pi over 2 squared. Negative sine of pi over 2 would be negative 1, because sine of pi over 2 is 1. That gives you negative pi squared over 4. That would be your slope. So essentially we're starting with y equals negative pi squared over 4x plus b. We put in pi over 2 for x, put in 0 for y. So you multiply that together, it's going to be negative pi cubed over 8. So when you move it over to add it to the other side, it becomes positive. So the b would be positive pi cubed over 8. So therefore, this would be your final answer right here. Negative pi squared over 4 times x plus pi cubed over 8. All right, let's see. Maybe I could graph this real quick. See how it looks. You can feel free to fast forward the video if you don't want to watch this part. And let me make sure my mode's in radians. All right, you always want to graph in radians. And got a lot of interesting looking graph. Oh, let me put the equation of the line in there. Negative pi squared divided by 4. Oh, well, divided by 4 x. And don't let that bother you in the calculator. The calculator knows that, in other words, the x is not in the denominator with that 4. We wanted it to be there, which we don't, we would put parentheses around the 4x. But so the calculator knows that it's not there. Pi squared divided by 8. Let me just double check that. I think that's right. But we'll correct it now before I graph it. Yes, no, okay, that looks good. So let me see. Oh, you know, I'm gonna change the scale of yeah. Let's change the scale to make this Yeah, I'm going to make these in terms of pi. I'll make it, yeah, because we're only interested in pi over 2. I'll go from negative 2 pi to positive 2 pi, and we'll scale it by pi over 2, so every mark will be pi over 2, and then we can leave the y thing alone. We don't care about the y. Now let's see how it looks. Because I want that mark where you normally see that first tick mark, I want that to be the point of interest there. Yeah, there it is. See right here. So there's that's pi over 2, 0, where that first tick mark is. All right, come on, tangent line. Well, that's a thing of beauty right there. I'm not going to worry about later. I may go back and paste this in the notes, but for now, at least if you're watching the video, you can see it. So there it is. That mark, that first mark on the x-axis, is the point pi over 2, 0, and that's a beautiful looking tangent line. It's just clipping it right there at that point. Remember, with tangent lines, we don't care if it intersects the graph somewhere else later. That's all right. We're just interested, is it only touching right, right, clipping it right at that point, without kind of, going through, slicing through the graph nearby or whatever. So, all right, well, that was fun. I enjoyed that. Find the points in XY form at which the graph has a horizontal tangent line. So notice sometimes it'll say just find the x values. That means we only want x. When it says find the points, that means you have to go back and get the y. So that just means anytime. Sometimes people will make mistakes and plug it back into the derivative. Always remember that to get a y value, you plug your x, if that's what you're looking for, a y value, it goes back in your original function, not any kind of derivative. It goes into the original function. The derivative gives you slope, and until we learn what the second derivative gives you later on. But for now, so we have to find the derivative, set that equal to 0, and then we find how many values we have, if there are any, how many x values, and we plug it back. Once you get the x, it won't be that difficult to plug it back in the original function to get the y. So we can see everything here now. So bottom, x squared minus 7 times the derivative at the top, which is 1, minus the top, x minus 4, times the derivative of the bottom, which is 2x, all over the bottom squared. So be careful. So that's 2x goes through here and makes that 2x squared minus 8x, but it's still trailing that negative right there. So you always have to be careful. So quotient rule is always going to have that negative there. And be careful how you combine the terms. So you have, basically you have 1x squared minus 2x squared makes negative 1x squared. And then negative, there's no other x's other than this one, so negative of negative 8x makes positive 8x. And then the negative 7 right here takes care of that. We leave the denominator alone. Now, when you're setting this equals to 0, it looks like this might be kind of complicated looking to do that. It will not be be that complicated, because, as Stewie says here, if you're solving a fractional equation that's specifically set equal to 0, you only need to solve for the numerator equal to 0, because that's what makes a fraction equal 0 if you think about it, right? It's the numerator, not the denominator. So like 0 over 6 or 0 over 10. Now another way you can think about this also would be correct is if you set this equal to 0 and you kind of did it and you multiplied both sides and got rid of the x squared minus 7, you'd still be left with that numerator. So either way, all you have to do is just, even though the denominator is technically part of the derivative, it's still part of the derivative right here. But the setting it equal to 0 part means we only have to set the numerator equal to 0. So just forget the denominator. So negative x squared plus 8x minus 7 equals 0. I like to change that negative to positive. Generally, these problems, and that's what I would do on a test also, is I would want them to be factorable. I mean, unless it was like x squared equals a number, like x squared equals 5, that's okay, because that's just plus and minus square root of 5. But that way we can avoid the quadratic formula. So this works perfect. Just take negative of everything, and it factors into x minus 7, x minus 1. So you have two values that make it 0, 7 and 1. But then to get, like I said, the problem's asking for the point. So if you plug 1 into the original one function back up here, you're going to get 1/2, because you'll get negative 3 over negative 6. As you put a 7, you'll get 1 over 14. You'll get 3 over 42. 3 over 49 minus 7, 1 over 14. So if it's asking for the x only, then we would have been done with 1 and 7. But if it wants the actual points, then you're looking for these two right here. You just plug them back in there to get the y value. And that's it. Okay, so it's just whatever it's asking you in the problem. If you're trying to get the point, you just have to take that one extra step of plugging your x into the original function. Higher order derivatives. All right. You can keep taking derivatives of derivatives. Pretty exciting, huh? If you take the derivative of a function, you can take then d dx, take the derivative of the derivative. Now, because of this idea of multiple derivatives and then how we'll use this, now we'll still say, obviously if we say we're going to find the derivative, that implies it means this is called the first derivative. But there's other applications, especially in chapter 3 with the graphing and stuff, where we'll be using both these first and second derivatives, that we will need to specify first derivative, second derivative. So up until now, it was just called the derivative. I guess that's similar to the when we had a First World War. I guess you didn't have to call it World War I specifically until there was a World War II. I guess, I don't know. Maybe that's a bad example, but now second derivative. So we use this prime notation, and then after this is another way to write the second derivative. Just you don't have to worry about ever labeling it that way, but it's good to recognize. So the third derivative would be the d cubed y over dx cubed. First derivative, second derivative, they use the prime notation. Then after the third derivative, they quit using the prime notation. And then they go to, now they write an exponent there, they put parentheses around it. That's very important. You need something to indicate whether they use parentheses or bracket or some sort of notation. You wouldn't want to just leave a 4 by itself, because that would look like it was after the 4th. But with parentheses around it, around the exponent, that's implying the derivative. I don't think I really asked you anything like this weird on this test, but it's kind of interesting. If you take, for a polynomial, some terms the derivative would never end. It would never go away to 0, but for this one, if you have x to the 99th power and you took the 100th derivative, that answer would be 0. I wouldn't worry too much about that. So I did this in Maple. So look at the 99th derivative is this big gigantic number. I mean, once you've taken the derivative 99 times, then you're out of x's. Because each time you take the derivative, the x will go from 99, 98, 97, so there's no more x's. And you're left with one big giant number. So obviously then the next derivative is the derivative of that big number, but if there's no x there, the derivative of any number would just be 0. All right. But, okay, I wouldn't worry too much about that. But all right, we've learned in a previous section that velocity is the derivative of the position function. And this is just for the following object example, but that's true for any kind of position function. The acceleration is the derivative of the velocity, or it's also the second derivative of the position function. Now, in other equations, it'll be something, more, this one, though, for this, it's always gravity. It's acceleration due to gravity. And you can take two derivatives. So this one, we had this function before when I talked about velocity. Now I can take the derivative with respect to t. So keep in mind that that's telling you your variable right there is t. That means everything else is just acting like a number. So the derivative of g times t would be like taking the derivative of 6 times t. It would just be g, and the derivative b 0 would be 0, so it's just g. So that acceleration is always constant due to gravity. But now here's an example where I'm giving a random position function for some sort of particle there, and so we can't make that assumption. Let's say we want to find the velocity and acceleration at t equals 2 seconds. So anytime that so it doesn't say instantaneous here, but whenever you're applying it only at a specific value, that's implied to be instantaneous. So it's instantaneous velocity and acceleration at 2 seconds. So it's not too complicated. Take the derivative of this function, which will be 3t squared minus 6t plus 8. Then you take the derivative of the derivative. So the derivative of 3t squared minus 6t plus 8. Derivative of 3t squared would be 6t. The derivative of minus 6t would be minus 6. So there's your second derivative, which is your acceleration function. So we have our velocity. We have our acceleration. So now we plug 2 into both of those. So put in 2 into this one, you're going to get 8. Plug in 2 to the bottom one, you're going to get 6. Now, I'm not picky about units on a test. I've mentioned this before. I'm not picky about it, but they certainly would be in a physics class or something like that, I would imagine. But I wrote the correct units here. Velocity would be centimeters per second, and then acceleration would be centimeters per second squared. So that's not too bad. Here's a problem where now so be careful what information it's giving you. Notice it's giving you the third derivative, triple prime, and it wants the fifth derivative. So you have to be careful that you realize that you don't take 5 derivatives like you would if you were starting with just f of x, because you're already at the third derivative. That means you only need 2 more derivatives to get to the fifth derivative. So we take the derivative of f third, which will be f4. So it's 3x squared plus 5. So negative 2 makes that positive 2. Subtract 1 makes that x to negative 3. And then take one more derivative. So the derivative of 3x squared would be 6x. The derivative of 5 would be 0. We have negative 3 times 2 is negative 6. Subtract 1 from the exponent makes that negative 4. Here's a second derivative problem. There's 2 of them in a row. X squared plus 3x to the negative 3. First derivative would be 2x, and negative 3 times 3 is negative 9, x to the negative 4. And then one more derivative, 2x would be 2. Negative 4 times negative 9 is 36. Subtract 1 makes that negative 5. So the second derivative, f double prime of x, would equal 2 plus 36x to the negative 5. Now we've got, of course, this one I certainly, after the second derivative, start getting out of hand. Yeah, well, actually, we couldn't really do the next derivative after this second one until we learn about what's called the chain rule, which is the next video after this one. Well, okay, we can start out with something we've already learned, secant. Secant derivative is secant times tangent. So far so good. That's just a rule we saw earlier. Now we have to apply the product rule to take the derivative of secant times tangent. You see I labeled each step here. So I'm going the order f prime g plus fg prime. So the derivative of secant would be secant tangent times the g, which is tangent, plus the secant itself, times the derivative of tangent, which we learned earlier is secant squared. So technically I put the flag there, meaning that that's the correct solution. That's right. But I just combined these loose terms just because I could. Multiply the two tangents together to make it secant tangent squared, and I multiplied those two secants together to make it secant cubed. Now that's only important if you're obviously if it's a multiple choice question and you're having to look for the right answer and it looks like that. So you would need to do that. Handwritten answer, I wouldn't care. But that was not obviously too difficult to do that. Okay, I find these problems to be kind of interesting. It's giving you some information. G of 2 equals 3. G prime of 2 is negative 2. H of 2 equals negative 1. And H prime of 2 equals 4. And there's 4 different problems. I chose 106 and 105, product and quotient rule. So what you have to actually do, and we're trying to find f prime of 2, is you need to set up the derivative in notation form here first. So if I take 106, f of x equals g of x and h of x, and just work with that, forget, and then we'll take care of the number business. So if I go product rule of g times h, I would have g prime of x times h of x plus g of x times h prime of x. Now I want to find f prime of 2, so then I can substitute 2 in there for all the x's. So obviously that since we don't have the original function, the only way this can be solved is based on that they gave us all these numbers up here. Otherwise we couldn't do this. So the only thing we can find is f prime of 2. We could not find, for example, f prime of 5. We can only get f prime of 2. So now that we've labeled this and then substituted the 2's, now we just come back up here and plug in every number that was given to us. So g prime of 2 is given negative 2 right there. H of 2 is given as negative 1. G of 2 is 3. And H prime of 2 is 4. So you multiply them together, you get 2 plus 12, 14. And that's it. So it looks kind of scary, but it's not that bad. It's really not that difficult. It's one of these things that probably looks more intimidating than it really is. The next one, if I went back to 105, G over H, so you just have to do a quotient rule. Okay, I went ahead and put the 2's in there, but so it's basically, it's H times G prime, so you can assume the 2's are already there. So bottom times the derivative of the top, minus the top, which is G, times the derivative of the bottom, which would be H prime, all over the bottom, which is H squared. So obviously if they had written this as H on top and G on bottom, it would have been a different result there. We still could have done it, but it would have been a different result with that information. So you see all the 2's are already there, so it's a matter of going back and find those numbers. H of 2, negative 1. G prime of 2 is negative 2, minus G of 2, which is 3. H prime of 2 is 4. And then over the bottom, it's H of 2 squared, negative 1 squared, which will be 1, so the bottom goes away. And you have 2 minus 12, which is negative 10. And that concludes this video for the product and quotient rule.